So today we are going to be discussing about missing data. We had this talk last year, but it was kind of really practical, and we did not cover some of the key concepts that precede practice. So today's talk is organized in such a way that we'll cover both the key concepts that are helpful for understanding some key aspects of how to implement missing data assessments in practice. And the presentation will give insights into different aspects of missingness, but also focus very much on the commonest two ways that missing data is handled, which is complete case analysis and multiple imputation. So we are going to look at why missing data matters, the causes, the types, the different handling approaches, how do we diagnose missingness, and using some data, we'll show how complete case analysis compares with multiple imputation. Also discuss the idea of sensitivity analysis, which is very critical for assessing missingness. And we might discuss on best practices and reporting at the end of the presentation. So the goal is that at the end, you should be able to explain why missing data matters and identify some common causes. You should also be able to differentiate between the different types of missing data and to apply appropriate handling methods. You should equally be able to evaluate and report missing data using some diagnostics and analysis methods. So when we say missing data, I think this is one of the most obvious ideas. You don't need to define it very much because the word itself kind of already explains what the concept is. So we'll dive directly into what the commonest causes of missing data are. And the first common cause, as we all know, is data entry mistakes or skip fields. I think everyone is very familiar with this, even if it's your first time that you've ever looked at data. The first thing you notice is that data is missing here just simply because that variable was skipped. And that usually happens at the stage of data collection. And so if people do not enter data in a field where they are supposed to enter it, be it on a questionnaire or in a tablet, you're definitely going to be having missing data. Secondly, you might have some kind of questions that the participants refuse to answer because these are very sensitive items. And usually you have this in studies that have sensitive topics like, for example, sexual behavior, depression. You are likely to get missing data because participants do not really feel very comfortable providing responses for those aspects. It could also happen particularly where you have some follow-up for you to have missing data because the participants have been lost to follow up or have dropped out of the study. And in that case, missingness will be the case. And we have this a lot in longitudinal studies. The next cause will be a failure in, let me say, device that you're using or because of poor internet connection. So you can imagine that if you have rolled out a survey and the participants are filling the form online, while filling, they might have a failure of their device. And in that case, you might have the data that they have entered so far saved or all of it missing. And so that's one common cause, particularly for online surveys, but it's also true for data collection that involves using devices like tablets in the field. So this will be one other way that it will get data missing. It could also be because the protocols and your SOPs for your study are too long and complex. And so your team or your data collectors never read them. And so there might be a particular way that you expect them to collect data. And because they do not understand that, they do not follow those protocols and hence miss a lot of data that needed to be captured. So it's always good to keep simplicity in your SOPs and in your methods for data collection. The sixth cause will be data transfer or different data type conversion errors. And I think this is a very common one, particularly when we are using like electronic devices which involve syncing data between the device and maybe the cloud or the server. You can have some obstructions at that level due to different reasons. It could be network, it could be the technology itself. And if that happens, it happens that there's a breach in the way that data moves from the device to the cloud, then you can have that aspect of the data missing. And lastly, it could be the way that you merge data. So oftentimes we have data available in different tables. And in trying to combine data from different tables into a single table, you can have mistakes. And this is quite common when you're doing data wrangling, data cleaning, and data exploration. So you have to always be very careful because depending on the methods that you're using, you might drop out some particular observations or entire variables in that process. So these are the different causes, common causes for missing data. And let's now look at why missingness is a critical issue. And the first thing is that missing data biases estimates, and this will distort the kind of estimates that you get. For example, imagine that you were conducting a study where you were assessing, let me say, depression in a certain environment, and several people that you interviewed refused to respond to some of your key questions. And so you end up maybe measuring the prevalence of depression in that group or in that study population. What you get will be based typically on the data that you observed, that is the data that you collected. But does that truly represent the entire picture or the true picture? Remember that there are some responses that you did not get. And if what you finally get in your analysis from the data you are able to collect does not look like the true value of what really is in the minds or in the reality of your participants, then there is bias. And that bias is a big issue because you're going to be sharing these results and disseminating them as the truth. So missingness deviates us from that truth in the reality. Secondly, missing data hampers precision and stability. And because of the way that we are going to be handling the data, we can be handling it through different methods. And one of the commonest methods that everyone uses is just to delete the observations that are missing. And if you do that, it means that your sample size is going to drop. And if your sample size drops, we know that you are going to lose power. What is power? Power just simply means your ability to detect the true estimate. And the slower your sample size, the lower your power is, or your ability to detect the true estimate that you are trying to measure. And one way that this reduction in power shows in your results is confidence intervals that are quite wider. You have models that are quite unstable. We are going to see this in the subsequent slides as we explore some practical scenarios. Lastly, it also hampers operational and strategic cost issues. Like, for example, if you have a lot of missing data, it means that you have to really do a lot of exploration. And so it makes your analysis slower. It becomes more expensive because maybe you have to go back and look at the data all over, go across all the different steps in the data exploration and preparation process. And you can also be in a situation where you have to discard a lot of data that is missing. And it costs a lot of money to collect all of that data. And that is not a very cost-effective way of conducting research. And also because you are using data that is not very representative, that is quite biased, the decisions that you draw or the inferences that you draw from this data are going to be skewed. And so you're going to have poor decision making from data that is incomplete. Now let's move to the second aspect, which is types of missing data. This is usually very complicated to grasp at first, but I will try to, as much as possible, to make it intuitive. So there are three key categories of missing data, or three different mechanisms of missingness. You have missing completely at random, you have missing at random, and missing not at random. Even from the names, you can start really understanding what this means. The key difference here is you have completely at random. So here you have missing at random and here missing not at random. So as you move from completely at random to missing not at random, you can see that bias is reducing. So let's look at these three uh, figures that we have here. What you have here in gray kind of represents missingness. So across the different tables, wherever you see gray, it means that there is missing data. So you can imagine this observed table as what you actually end up with after your study, the Excel sheet before you. And then unobserved data is data that is missing, data that you did not collect. But we know that that data exists in reality. You just did not collect it. And so I'm putting them side by side for you to get the intuition of the idea. So if you look at scenarios where data is missing completely at random, you notice that there's really no pattern of missingness, both for the observed data and the unobserved data. So we say the probability of missingness is unrelated both to the data you're seeing on your Excel sheet and the data that you could have collected that you did not collect. On the other hand, in the missingness at random, you start to observe that there's somehow for the observed data, the Excel sheet before in your computer that you're looking at, you notice that there is some pattern among the data that you have. For example, you see that the gray missingness here are kind of related to maybe the light missingness schedule, missingness in the other variable. So there is somehow among observed variable, there is some link between the missingness. So missingness can be explained by some other variable in your data, but that is not due to some unobserved data. So in the last case where you have missingness, missing not at random, uh, the missingness has no relationship within the data that you have before you. But what could explain the missingness lies in the data that you did not collect. So let me try to drive this more concretely with some practical example. So let's imagine here that you are in a clinic and you've tasked your nurses to collect data for participants at the reception. And they collect very basic data on a simple paper or on a document, and they collect age, sex, age, systolic blood pressure. So this is the data that they collect directly. And then let's just add the hypothetical scenario here, which is the unobserved data. What could have been the possible complete data if they had collected it? So this cell shows you missingness. Generally, in statistical software, missingness is usually represented by NA, which stands for missings, like where that missingness is shown in most software. So in a case where you have missing completely at random, we notice that really the way that the data is missing is completely at random because when we look at it, we do not see any pattern in missingness. The missingness in this systolic blood pressure column is unrelated to any other variable here. And even if we were to know which we really never know in practice, that we can kind of infer, as we will see in the last example, if we knew, we could see that maybe it's just random. It's unrelated to both what we see and what we do not see. It's purely random. So you can imagine, for example, in your clinic, it happens that the nurses that are there, sometimes someone went for break and didn't collect the data, the blood pressure values, or maybe the BP machine had a problem. And that is totally random. In that way, you are going to have observations that you do not correct. So in the second scenario, let's now imagine that you had missing blood pressure. But in looking at the data that you have before you, you notice that the blood pressure was missing for younger people. So now we know that missingness is kind of related to age. And so you can say systolic blood pressure is maybe not measured a lot because when nurses see people who are younger, they often think blood pressure won't be a big deal for them and so don't measure. So there is missing at random. And we know that it's missing at random because the missingness is kind of related to some other variable in our data. In the last case scenario, we have data that is missing in the systolic, but there is, among the data that we have before us, we do not really have a pattern. But somehow it happens that there is a reason really why that data is missing, which is related to the variable itself. Like for the case of blood pressure, it could be that people showed up at that clinic and they were in hypertensive emergency. And since it's an emergency, once they did the first measurement, they just started going into interventions, trying to reduce the blood pressure because it was urgent and they didn't collect that data. In that case, missingness is not at random. It is because we knew the blood pressure and we kind of avoided, focused on something else. And the rise in blood pressure itself explains the missingness. Another way that you can understand this, imagine like in a clinical trial and you are assessing a treatment effect, and then some participants do not come back to the clinic for you to measure the effect the treatment effect, because maybe they have some side effect. You can see that the missingness is directly related to the treatment itself. So let's move now to how do you handle missingness conceptually. And I'll talk about three different broad categories of different techniques for handling missingness that you can use. And the first one would be just ignoring the missing data. So this is kind of the commonest one. So let's look at the first type, where we have list-wise deletion. This is the commonest one, also called complete case analysis, where you remove the entire rows that have missingness. So if there's any missingness, you just remove the entire row. So you see, like in this example, there's missingness here, we remove it. And notice that it reduces the number of observations from 6 to 4. So your data reduces. In the second type, we have pairwise deletion, where you are kind of doing analysis on a subset of the data. So you pick maybe two variables and you reduce missingness for only those two variables. So unlike the first type, where you remove any row that has missing data. For this, you select first the variables and then you remove the missingness. So here, missingness, we're interested in sex and age, and we just remove missingness only for those variables. So in the third category, you could totally just remove the entire column or the entire variable because there is usually too much missingness. Some people suggest that if you have more than 40% of data missing in a variable, you could just exclude that variable. But take note that you have to be very careful because that might be very critical data. And in that case, you have to consider other ways that you could handle it. So what you should note from this first category of methods for handling missing data is that all of these three are valid if data are missing completely at random and the amount of missingness is not very much. And this is the case because when data is missing completely at random, as we saw earlier, the data that you have is quite representative of the true estimate. And so even if you remove some of those observations, the picture of what you are going to get still reflects the reality. Let's go to the second category of ways of handling missingness, which is now replacing the missing value, not deleting it as in the first category. And this replacement is usually called imputation. You're imputing. And you could do single imputation, which means you are just doing single replacements in data. And there are various ways that you could do single imputation. And I'm going to just select three key ones to discuss today. There are other ones, but these are the commonest ones. The first is mean, median, or mode imputation. And so if you imagine that you have missingness as shown in this figure here, you can just replace the missing value with any measure of central tendency. For categorical data, you could do this by looking for the most frequent category and just replacing it with it. You can calculate the mean or median and then you replace with it. So that's mean, median, single imputation. The second type would be for you to replace it with a method called last observation carried forward or the next observation carried backward. So again, look at this example here. We could just take 27 and we move it in front. And in that way, we replace the missingness with what the last thing we had. And we could also just take 34 here, and then we fill the missing data before it. So that's next observation carried backward. This method could be applicable particularly in longitudinal studies, where, for example, if you were measuring people's weights and someone missed a weight measurement, is missing a weight measurement in a particular visit, you can just take their last weight measurement or the previous one and use. And the third type, I learned this from Prof. Don and Prof. Chuhu. In your assessment, because maybe you have too much missing data and you are worried, you could just actually just create a variable, particularly for categorical variables, and just create a new variable called missing. This will really help you to solve the problem of a reduction in power. So instead of removing entire rows, you could just fill it with something like an indicator saying missing. And in that way, that aspect is filled, and then you don't have to remove all of those rows. So what you should also note here is that all these single imputation methods underestimate variability and hence risk biasing the results. Why? Because you are adding single estimates here that are coming from other data, there is usually some variability or variance that exists with regards to each true measure. And because you are just taking the mean value or a related value and putting in there, you are missing that variability. And because you are missing that variability, it really has a lot of influence on the effect size that you're going to get. As you know, whether you're measuring odds ratios, confidence intervals, and all of those different effect measures, you need aspects like standard errors and so on. And so single imputation has that problem of underestimating those variances. And so that makes it a very limited approach for correcting missingness. And the third category, which is actually the gold standard for handling missingness, we do multiple imputation. So unlike single imputation, we do multiple imputations, so repeated imputations. And I'm going to show how that process works. So you start with incomplete data. So this could be your Excel sheet that you have at the end of your study. And your goal is to really avoid bias. You want to make sure that you replace the data that is missing, but avoid bias as we saw in the first category where we just delete things. And also solve the problem of data loss because you don't want to reduce the sample size and your power. And also solve the problem of single imputation. You don't want to lose the variability in your data, which really has a lot to do with the accuracy of your estimate. So what do you do with that data? You take your incomplete data and you do imputations, not one single imputation. You create multiple different sheets and you complete the data in those sheets. So these are like kind of like 1,000 different possible ways that that missing data could have been collected. So the algorithm kind of simulates the different possible values that could be inside those missing cells. And it does not make only one, it makes multiple copies and fill them with missing data, with some data. And does the algorithm get the data? It gets it by using some regression models. And so the way that we usually create these different data sets and impute missing values into it is through something called multiple imputation through chained equations. There are other ways that you could do it, but this is the commonest way. It's called mice, and there's a package in R for doing mice imputation. So you just have some regression models among the different variables that are in your data, and that helps to predict what the missing value could have been, and it creates multiple of these sheets. And so what do you do next? You now take for each of the sheets that it created and imputed data on, you do the analysis. So if you were, for example, doing a logistic regression model, you do logistic regression models on each of the separate data sets, and you analyze each imputed data set separately, and you get its own estimate, its confidence interval, standard errors, and everything else separately for each of those data sets. This is where it gets interesting. Because you have different results, you need only one result. So you have to pull the results together. So you combine all the estimates or all the analysis results that you have from these different data sets and you collapse it into one single pooled result. And we do this by doing something called Rubin's rule. So this is actually the guy who has done a lot of work on multiple imputation long time ago. And so, for example, if you are calculated odds ratios in each of these data sets, you can take the mean odds ratio for each of the variables. And the nice thing about Rubin's rule is that you also take into consideration all those variances, like the standard errors that you use to calculate your confidence intervals and the rest from it. And this kind of helps produce really some valid estimates and confidence intervals as compared to just single imputation of your data. So to summarize, what we have here, the type of missingness and some way that you can handle it. And I've bolded here the commonest ways that we go about it. Uh, this is not a very strict protocol as to the method for handling what type of missing data, but it's for you to have a sense of what are some of the methods that are acceptable or how you could be thinking about it. So you have data that is missing completely at random, so you know that the missingness is purely at random and that the data that you have is quite representative. And in that case, if you do not have too much data missing, you could just only analyze the data that is available. And we call that method, as we saw, list-wise deletion. And another name for list-wise deletion is complete case analysis. So you analyze with the complete cases. You could also do some simple imputation, mean median imputation, mode imputation, last observation carried forward, and so on. But you have to be very sure that data is missing completely at random. And this is the least common, one of the least common ways that data could be missing, because in reality, data will hardly ever be missing completely at random. So I would not suggest that you think about this as being a missing mechanism. And that explains why just doing complete case analysis is quite worrisome. And unfortunately, complete case analysis is kind of the default method for handling missing data in most software, and it's actually what the majority of people are doing. And so it's a concern. So the second type, if you have missing at random, which is actually the most common form of missingness, you can do multiple imputation, particularly multiple imputation by chain equations, which is often the go-to method in most analysis software. There are other techniques that you could use, but multiple imputation is the way to go. So you have missingness not at random, which is also very, very hard to know because you have to know the scenario or the nature of the data, of the unobserved data, the actual missing data. And the ways that you can know it is really think very clearly about how the data was collected and to do some form of sensitivity analysis. And there's a particular method called delta adjustment where you move the imputed data gradually and you assess how the model changes and so on. So these are some of the ways that you can think about it. So how do you assess this in practice? We've looked at the theory. And in practice, you could think about it using these steps. And the first thing is always to really try to understand what the cause of missing data is. In our earlier slide, we had reviewed the different causes. And it's very important to even look at the study design, because the study design might just be telling you maybe where the missingness could be coming from. It could be from the way that your SOPs and protocols are, or the way that your data is collected. Maybe you are using papers and some of the papers got missing. You're using a tablet, sometimes the tablet malfunctions. Yeah, you have to have all of that background information. And it's always, in my opinion, one of the most important considerations to think about. If you have a lot of, for example, if you have a lot of CD4 count data missing, this could just be because we have moved on to a new algorithm in HIV programs where we do test and treat. So we are not systematically measuring CD4. And of course, CD4 data will be missing in data that is collected from such a clinic or in a typical HIV clinic in Cameroon. And so that background is very critical and it's a very essential first step when you're thinking about where the missingness is coming from and how you can potentially assess it. So let's say you've done that. The next thing is to actually start looking at the missingness itself, the distribution of missingness. And so you visualize it. We'll look at some examples in a moment. You do heat maps, you do missing data matrices, and so on. There are some statistical methods that you can also use to kind of have a sense. And a particular specific test for missing completely at random assessments, it's called Little's missing completely at random test. And because missing completely at random is really not a very practical cause of missingness, it's a very rare cause. Many people don't usually do this. And another way that you could also use statistical methods is to actually compare both observed and unobserved groups. So what this means is that you organize the data in such a way that you can classify all the observations by whether there is missingness. And so, for example, if you have like a BMI as a measure of your key outcome, you could look at participants, you could create another variable, which is participants missing BMI versus those who have BMI data. And then you compare other variables, covariates, predictors, by this new outcome missingness indicator. And you can use tests like chi-square test, t-test, and so on to compare. We'll look at an example in a moment. And you can even go as much as even doing more advanced methods like modeling, where you take this missingness indicator for that variable and you do logistic regression to see whether there is some association between some of those variables and the missingness. And this can actually help point to you whether this is missing at random. Remember, we said missing at random, there is kind of some relationship between missingness and some other observable data in your data. And this could be a way that you could really tell if data is missing at random. And remember, missing at random is the commonest form of missingness in real life. So let's look at some of these examples. So this is, you could get this kind of plots from these packages in R, Vim, Narnia, ggplot2. So we have some data on obesity from IDEA. And you see if you run this code in R, this is what you get. It looks at all the different columns or all the different variables that you have, and it quantifies the missingness. So you can see, for example, duration on ART was missing here by a substantial proportion for this particular variable. And you see that age data was probably very, very complete for most participants. This other approach to visualizing the data is very interesting because it just looks like looking at an Excel sheet that you have zoomed in very closely. And so the dark spots kind of show what's missing and the gray spots what's present. And so you can see for a given variable like age here that is very much present. A variable like viral load here is missing significantly. CD4 count is also missing significantly. So a snapshot view of this could really give you a sense of the variables that will be very troublesome in your analysis. You could also analyze missingness by another variable. So for example, we look at missingness by the year of enrollment here, and we look at it by some few variables. You can see that as you move from dark here towards yellow, it gives you a gradient of the extent of missingness. And for something like fasting blood sugar, we can see how availability of data is over the years. So these are just a few ways that you can visualize and have a very good sense. And from this visualization, you can really go back and ask, how was CD4 count in this case? Why is it missing? How was it collected? Going back to your method, talking with the staff at the clinic, your data collectors, to have a sense of why that missingness is there, which gives you an idea of the missingness mechanism. Also, you could also do the comparison by a missingness indicator. So you create a missingness indicator, you look at, you take a particular variable, and I gave the example of BMI in your data set. You look at people who are having BMI data and those who do not have. So observed is those who are available, missing is those who are not there. And then you can use some statistical tests to compare them. So you can see an example here. We choose some few variables: age, sex, alcohol, before count, and viral load. And because maybe in this analysis, BMI is our key outcome of interest, we want to look at whether missingness in this key outcome is related to some other variable in the data. And we see that there's actually statistically significant difference across these different variables, which kind of hints to us that it might be true that this missingness might be related to some other observable data in our data set. And we are going to see in this chart that that's really quite true. And so one way, why this tells you statistically significant differences, it doesn't tell you the magnitude. So for you to be able to tell the magnitude or the extent to which missingness for each variable influences maybe the outcome or another given variable of interest, you have to quantify it. And one way you do it is by measuring the standardized mean difference. So let's take, for example, in our same data set, we took the group of people who had the data on BMI, and we take the people who do not have data on BMI. We can take for each variable, like for example, the age group, we could calculate like the mean age between the two categories. That's the people who have BMI and those who are missing BMI. And we standardize it by the variance in such a way that we have one single unit. And we repeat that for different other variables. And then we compare where that stands on a certain scale. And on this diagram, you have the different variables, same as we have here. And on the x-axis, we have the standardized mean difference. That is the difference in the mean of each of these values across what we observe and what is missing. And so for the CD4 value, for example, we see that we have something like 2.3. And usually 0.1 is kind of used as a standard point for doing that assessment. We see that 2.3 really is very far away from 0.1. And this huge deviation amplifies it, gives us in terms of what extent is CD4 influencing missing BMI data. And we see that by a huge deal, by about 1.3. And so it means that we should really be careful about this CD4. And we saw it in the visualization earlier. You see that a lot of CD4 count data was really missing. On the other hand, if you look at alcohol data here was quite present. So the missingness in BMI data is not very much related to alcohol. So these kind of assessments can help you spot some of the variables that would point to the fact that data is missing at random, meaning that the missingness is explainable by some other variable in your observed data. Now, let's imagine that we were building like a logistic regression model or any other kind of model. Could be a Cox model, could be any other type of statistical model. And ideally, what you want to do if you are to you do your complete case analysis, as typical software will do. At the same time, you conduct multiple imputations and you compare both data sets. So we're actually going to look at an example here. So sorry, let me put all of it on. So here we have a model that we have developed, and this is looking at factors associated with overweight and obesity. And these are the different predictors that we've included. And on this other side, so this complete case analysis model has one single data set. On the other side, if we do multiple imputation, as I've shown, it's going to create several different data sets, run the logistic regression on each imputed data set, and then pull the results. So in the complete case analysis method, it uses the method of listwise deletion or complete case analysis. And so it deletes all the rows that are missing data. And so what happens is that if it deletes all the rows that are missing data, a lot of the rows are just going to go away. In our visualization that we saw earlier, we saw that there were variables that were missing significant number of observations, and CD4 count was one of them. And we have CD4 count and viral load in this model. So all those missing CD4 and viral load will automatically be taken out. And so in this model, we see that the model includes only 606 out of 9,556 participants. So this complete case analysis utilizes only 6.3% of the data. On the other hand, if we do multiple imputation, we fill all those CD4 and viral load missing data, and we do that for other variables that are there. And so we don't lose any single row for observation. And so we retain all the estimates. Let's look at what will happen in terms of the results when we run the analysis. So here are the results. So this is what we get from the complete case analysis model and what we get from the pooled multiple imputed model. So the things that you have to notice when as we assess this is the odds ratios, which are the effect sizes of interest on this column. So you compare the one here and the one here. You look at the confidence interval width. Last week, Dr. Bache was talking about, Meve was talking about effect sizes and precision and so on. And we said wider confidence intervals are a problem because they show that our estimates are not precise and they can indicate other things. We also look at p-values, which are on these columns. And let's compare, let's take, for example, H here. We look at the odds ratio here, 1.22 in the complete case analysis, and we compare that with the multiple imputed data. We notice that the odds ratio kind of went up. Also notice for all of these different categories, it changed for all the different categories of H. Notice here also the confidence interval bands or the widths. They are very wide here. You have 0.48 to 3.24. Here, it's much tighter. So you see, it starts from 1.72 and then 2.43. So it's like the confidence interval has come closer, which means the results are more precise. And this is so because the sample size is bigger. Remember, in the multiple imputed model, we are using all the data, all the observations, because we imputed or replaced all the missingness with some plausible values. And consequently, also notice that the p-values have become statistically significant. And so this is one way that the multiple imputation can really improve the results significantly. So the key takeaway from here, and the results are applicable for other variables. I've used H, but you can observe the same thing for the other variables on the table. And so the key takeaway here that you should note is that complete case analysis usually wastes a lot of data, particularly when you have huge amounts of missingness. And so your results will be weaker, as we have seen in terms of the effect size and the confidence intervals, while multiple imputation kind of keeps a lot of the data. And the complete case analysis, because of a reduced sample size, you have lower power, wide confidence intervals, p-values that are quite unstable, as we can see here. The multiple imputation, we have improved power, confidence intervals tend to narrow, and you have p-values that are more statistically significant and associations that are more valid in terms of the effect sizes. So that I think you now have a very good sense of how this works. The other thing that I think is very critical for you to think about when you think about missingness is sensitivity analysis. This is very crucial. And all the different things that we've looked at so far have to do with some form of testing different strategies, which is already sensitivity analysis, trying one method and trying to explain where the differences are coming from. So to formalize it, note that you have to think about it in a very structured way. And the first thing you have to note is that it is usually very difficult to know the true missingness mechanism. And if you have to decide between the three, the one that is most common will be missing at random. The missing completely at random is not so obvious to detect and usually less likely. And then the missing not at random is also quite hard to detect. And for you to ascertain that is very difficult. So you have to think very well about how your data was collected. So having this difficulty in mind, always try to check if the results change. So for example, you do your complete case analysis as you guys usually do, but also do a multiple imputation to compare to see whether there's too much variation in the results. And you also run some of those visualizations. You also run the comparison to chi-square tests, standardizing indifference, and so on. And comparing the results can tell you whether missingness is really influencing. Imagine that if missingness is not really a big deal, if you run one form of handling missing data and run the other, you shouldn't see too much differences in the results. So the more there's variation, the more you should really think about the source of missingness and proper ways that you can handle it. So we recently published this paper. We're looking at how missing data is reported and handled. And I think this has really been a big revelation for us, that this issue of missing data, the scientific community is not taking it very serious and is very much neglected. And given all the reasons that we've outlined earlier, or the implications of missingness, it's very critical that we take this idea of missing data very seriously. We found that only about a third of studies had reported missing data, means studies that assessed comorbid hypertension and diabetes in people with HIV. We also noticed that a lot of missingness was due to CD4 and viral load. And CD4 is quite obvious, because of the test and treat. We also noticed that very few studies, there's very, very few studies, had discussed how missingness biased their results and conclusions. And if you do not transparently discuss this, then people should be careful about your findings and your conclusions. And of all the studies that reported missing data, less than half of these studies reported how they handled missing data. So it does not suffice only to handle it, but you must also report it very well. Most people, as you would expect, use complete case analysis, and only about 5 studies, which is like less than 10%, had used multiple imputation. So I think this is a very strong takeaway that we should take handling and reporting of missing data very, very serious. So these are some of the resources that you can check. And thank you very much.